All right. Hello. Hello. Let's go ahead and do some improper integrals. All right. Cool. So we got 5 improper integrals here, and then we have a more general problem that's actually really interesting conceptually that we'll work through here. Okay. So let me go ahead and get rid of this countdown and get the show on the road. So as with most of our problem sets, it's kind of a list of integrals, right? That's sort of how these last few days just are. So, problem 1. Part 1 here, we're looking at this integral from 3 to infinity of, I think I wrote dx over x cubed. All right, so we want to look at this and see, does this converge or diverge? If it converges, what does it converge to? If it diverges, point that out. So let's do this. So the bottom here, so one thing, when we're doing these improper integrals, there's really a couple things we want to look out for. Infinity or negative infinity in the bounds, obviously. But also we want to make sure like the function's defined everywhere. Like we're not dividing by 0 or something like that. So in this case, this wouldn't be defined at x equals 0, but it is defined on this interval, so we're good to go. We just have to deal with the infinity. So this will be the limit as b goes to infinity of the integral from 3 to b of, I much prefer this to be written as 1 over x cubed. And in fact, maybe we should rewrite this more to make it easier to integrate. This will be x to the negative 3 dx. Okay. So, integrating this, right, this is something we know how to do. So this is limit as b goes to infinity of, so we want to add 1 to the exponent and divide by that. So negative 1/2 x to the negative 2, right? From 3 to b. All right, so now we're just going to plug in this stuff, and I'm going to change that negative 2 exponent back to 1 over x squared after I plug stuff in. So this is limit as b goes to infinity of, right, so this will be negative 1/2 1 over b squared, right, plus 1/2 1 over 9. Okay. Now again, it's plus here because of that negative sign. It's going to be minus negative this stuff. In fact, maybe let's go ahead and write that just to make it a bit clearer. Right, so we're looking at this. Okay. So here, this part, when we take the limit, we're going to get 0. And then over here, this is going to be plus 1 over 18. So 1 over 18 is the overall answer. Hopefully that looks good there. Any questions? All right. So let's go ahead and jump over to the next problem. Next problem being the integral from minus infinity to 6 of e to the 2x dx. Okay. So for this one, we have the negative infinity in the bottom, and otherwise, e to the 2x is always defined, so we don't have to worry about any discontinuities. So let's go ahead and I like to use a for the bottom bound, but it's completely up to you what you want to use. You can call it literally whatever you want as long as that letter's not already used somewhere. All right, so we're looking at something like this, and let's go ahead and compute this integral. So this is the limit as a goes to negative infinity of 1/2 e to the 2x from a to 6. Let me make sure that really looks like a 6 and not a b. I don't want it to be confusing there. All right. So we're looking at limit as a goes to negative infinity of, let's see, here we have 1/2 e to the 12 minus 1/2 e to the 2a. That's what we're looking at here. This first part, when we do the limit, that's not going to be touched at all. Right? So this is just a constant, so it can come out. This thing here, e to the 2a, as a goes to negative infinity, what we're going to wind up with is e to a larger and larger and larger negative power. So it's going to be a really huge negative power, which means it's going to go to 0. This is minus 0. So our final answer is 1/2 e to the 12th. And that's that. All right. Any questions about that one? Okay. Awesome. There's no questions. Go ahead and do problem 3. All right, so problem 3, sorry. All right. Problem 3 here. Let's go ahead and write it down. This is the integral from 7 to infinity of dx over x plus 1, 1/3. Right. So again, we want to keep an eye out for places where the integral has infinite bounds and where the integrand, the function we're integrating, is possibly undefined or discontinuous. So here we have that that infinity in the bound. Okay, so we're going to have to deal with that. And here, this would be undefined at x equals -1, but that's not inside this interval, so no need to worry. Right? We don't have to worry about it. So let's replace that infinity up top. Okay, let's see here. This is going to go from 7 to b of dx over plus 1 to the 1/3. So when we integrate this, let's see, this is going to be 3/2 x plus 1 to the 2/3, 7 to b. This is what we're looking at here. Okay. Okay. So let's plug this stuff in and see what happens. So limit b goes to infinity of 3/2 x, or sorry, not x anymore, b, b plus 1, the 2/3, minus 3/2 times 8, 2/3. So what's going on here? Well, this part, or let's say this part right here, 8 to the 2/3 power is 4, because it's cube root of 8, which is 2, and then 2 squared is 4. So this is 3/2 times 4, so whatever it is, it's something minus 6. Right? This limit here, b plus 1 to the 2/3 power, it grows somewhat slowly, but it does go to infinity still, because this is a positive power. It doesn't matter how small that positive power is, as long as it's still positive, this kind of thing is going to go to infinity. So, infinity minus 6, which is, of course, just infinite. So what we would say in this case is the integral diverges. Okay. And that's, again, because an integral is going to diverge anytime this limit here is, you know, infinity, negative infinity, or undefined. Right? The way it converges is if it actually equals a number. Any question here? Hopefully this all still okay. All right, cool. So let's go ahead and look at the next problem. Problem 4, or part 4. Okay. So part 4, we're looking at something a little more interesting now. Which is 1 to infinity of dx over x squared times x minus 1. I have to think about something for a second here. Have I... I'm trying to think if I made a little mistake here, and this is a type of integral we haven't talked about yet. We do this one. Okay, actually, we might. This one might be a bit tricky for us to do. This requires a technique called partial fractions, which we haven't actually talked about. Which might be a good option for Friday, actually. All right, yeah. I think when I picked this problem, I was thinking something else. So let's. It's a shame because I wanted to do this one. All right, let's change this a little bit to x minus 1 cubed. Yeah. All right, let's do this instead. Made a little mistake. We can't actually do that integral the way I had it yet. Okay. So to do this one, right, what we want to watch out for is, again, where is this function possibly undefined at? And where do we have infinite bounds? Well, we have infinity in the bound here, so we have to handle that separately. But this bottom is undefined when x equals 1, and that's the bound over here. So we have to keep an eye out for that as well. So since we have both bounds here are kind of problem points, we have to split this integral up. So I'm going to split this up to an integral from, say, 1 to 2 to keep it simple. Right? And then plus 2 to infinity. Right? So now each of these integrals only have one problem. And now we can use our usual technique here. Okay? So this one here, we're going to do limit as a goes to 1. And in this case, we have to approach from the right side. Right? Always important to keep that in mind. So this is a to 2. Dx over x minus 1 cubed. Plus, over here, we're going to do the limit as b goes to infinity, the integral from 2 to b. of dx over x minus 1 cubed. All right. So all right, so when we integrate this, this is going to be negative 1/2 x minus 1 to the negative 2, right? From a to 2, plus limit as b goes to infinity of, again, negative 1/2 x minus 1 to the negative 2. Right. Hopefully that looks good. Questions there? All right. Oh, sorry, I forgot to put the limits. All right, so now we're going to plug all this stuff in and see where we go. The limit is a goes to 1 from the right. Let's plug our stuff in here. So here, when we plug in 2, this is 1 to the negative 2, so this is just negative 1/2. And then we're going to have minus, so plus. This is 1 over 2 a minus 1 squared. Okay. And then over here, we have limit b goes to infinity. Here, again, we're going to have negative 1 over 2 b minus 1 squared plus that's going to end up being minus negative 1/2, so plus 1/2. All right, so now the question is, what happens at these two limits? All right. So here, this first one, this negative 1/2 is going to hang around. We'll discuss this in a second. This one here is quite easy, this limit. As b goes to infinity, this has to go to 0 because the bottom's just getting larger and larger. Right? So this is 0 plus 1/2. Now the question is, what's happening here? What is this doing as a goes to 1 from the right? If you think about that graph, right, the graph of that function, and in fact, maybe it's a good idea, let's plot this in Mathematica here. I think I need to reset this up. Yeah, that's all sorts of not captured properly. Let's see. Okay, there we go. So let's go ahead and plot that function. So we're going to plot 1 over 2 a minus 1 squared. Right? And we're interested as a approaches 1 from the right. So we're going to plot from 1 to 2. Right? So we're going to have 1 be on the left side, and we're going to have a little bit of stuff to the right, and we just want to see where the graph is trending. So if we look at this, if we follow this graph here, we see that as this goes off, as we get closer to 1, so 1 is where this axis is crossing right here. This axis is at x equals 1, or a equals 1. We can see that this is going off to infinity. So this limit in the problem, there's my mouse cursor. Yep. This limit of this part here is infinity. So this whole answer is just infinity, and so the integral diverges. All right. Integral diverges, and that's that. All right. Any questions there at all? Sorry, give me 1 second. Okay. Let's get back to this. So any questions at all about these so far? Okay, cool. Let's go ahead and look at the next problem, problem 5. Right. Last one here, we're looking at the integral from 0 to 9 of dx over x minus 1 to the 1/3. Right? And we want to know, can we integrate over this? Will this be okay? Right? So, again, we need to look for any place that the function could be undefined, and then we need to look for any infinities in the bound. Well, there's no infinities in either bound here, so we're good on that front. On the other hand, look at the x minus 1 here. This is this x minus 1, we get a 0 in the bottom when x is 1, which is inside this interval. So we have to split this up at x equals 1. So the way we do that is say, well, all right, integrate from 0 to 1. And then from 1 to 9. Right? We have to split the integral there because there's a problem. Right? So now that we've done that, what we need to do is we need to take limits to 1. So here, this first one, this is going to be a limit as b approaches 1, this time from the left, because we're starting from numbers less than 1. Right, and this is from 0 to b of dx over minus 1 to the 1/3. Oh, we already exactly did the same one, didn't we? Oh, that was to the 3rd. Wow, I unintentionally picked a lot of similar problems. All of these are like to the 1/3 or to the 3rd. Sorry about that. But the process is similar anyway. So plus limit as a approaches 1 from the right of a to 9 dx over x minus 1 to the 1/3. Right, so now we got to do this integral here. I got to move this back over here so look at the right spot. Right, so we want to do this here. Let's compute our integral. Right, so limit as b approaches 1 from the left. Here, when we integrate this, we're going to have 3/2 x minus 1 to the 2/3. This is from 0 to b. Plus, limit is a goes to 1 from the right of, is also 3/2 x minus 1 to the 2/3 from a 9. Okay. So now let's plug all our stuff in here. Limit as b approaches 1 from the left. This is going to be of, we got 3/2 b minus 1 to the 2/3. And then when we plug in 0, so we get minus 3/2. This is negative 1 to the 2/3. Right? Here, limit as a approaches 1 from the right of 3/2. This is 8 to the 2/3 minus 3/2 a minus 1 to the 2/3. Now let's try and deal with all this stuff. So this first part, again, I'll leave the gap here for now. Let's compute the actual numbers. So negative 1 to the 2/3 is just going to be 1. So this is something minus 3/2, right? I thought I heard a knock at my door. But I must just be hearing things. All right. Plus, again, let's write this number down. 8 to the 2/3, remember that's 4. So 3/2 times 4 is 6. And then we're going to look at this here. So this thing here, when I plug in 1, this function, this b minus 1 to the 2/3, this has no issue at b equals 1, right? We can just plug that in. No problem at all, because we're taking third roots here. So, this is just going to be 0 when we plug that in. Right? No problem at all. And same thing here. If I were to plug in a equals 1, this is perfectly fine. Right? And again, 2/3 power, there's nothing wonky going on here at all. This is nice and continuous. So this is minus 0. So we get 6 minus 3/2, which is 9/2. Right? And there we go. And that's it for this example. Any questions about that one? All right. So let's go ahead and move on to problem 2 here. Problem 2 is quite interesting. All right. We want to know for which values of p does this integral converge or diverge. Right. So let's go down a couple of the ones we've done so far. Right? We've computed this integral when p is 1, when p is 2, when p is 3. And here it diverged, it converged, and it also converged here. Right? We did these two in the lecture videos, and we just did this one at the start. Well, we did from 3 to infinity, but changing the 1 to a 3 doesn't change it. So let's do we've also kind of sorted out that if this is 1/3, this is going to diverge. Right? We kind of showed that if you go back to part 3, it was x plus 1 to the 1/3 power on the bottom, but it works out the same way. So this kind of suggests a split, maybe somewhere around 1. So here's what we're going to do. We're going to say, well, what if p is less than 1? Right? Well, actually, let's start here. Right, so the integral, let's just look at the antiderivative of 1 over x to the p. Okay? So this is the antiderivative of x to the negative p dx, which is, x to the negative p plus 1 over negative p plus 1, technically plus c. This is as long as p is not equal to 1. Right? If p equals 1, we have ln, which is a whole other thing. So here we're assuming p is not 1. All right? So, and it's fine. We already know what happens when p equals 1. So let's say here, well, what if p is less than 1? Okay? If p is less than 1, then this integral from 1 to infinity, 1 over x to the p dx, right? So we're doing limit as b goes to infinity of integral from 1 to b, 1 over x to the p. This is limit as b goes to infinity of x to the minus p plus 1 over minus p plus 1. Okay? From 1 to b. Right, so let's plug all this stuff in, and what we get is limit as b goes to infinity of, let me swap the order of the power up here. So instead of negative p plus 1, let me call that 1 minus p. This will be b to the 1 minus p over 1 minus p, and then minus 1 over 1 p. All right. So if p is less than 1, then 1 minus p is greater than 0, right? We just subtract that p to the other side. That means that this is a positive power, and something x to a positive power as x goes to infinity is infinity. So this integral here is actually infinite. So what that means is the integral diverges if p is less than 1, right? And we actually know it diverges if p equals 1 as well. But what if p were greater than 1? Okay? What if that were the case? Well, the good news is we don't have to really repeat a bunch of work here. Everything's the same up until right here. So instead of redoing all that work, let's just go ahead and copy this back down. Okay. So we're going to go right back to here, because all that work's going to be exactly the same. It's not going to change. Now the difference here, though, is that when I move the p to the other side, I find that 1 minus p is a negative number. Right? Since this is now a negative power, this means as b goes to infinity, this part's going to go to 0. So this is going to be 0 minus 1 over 1 minus p. Okay? So in particular, if I absorb this negative into the bottom, let's say this is 1 over p minus 1. So this integral, we could say the integral, converges to 1 over p minus 1 if p is greater than 1. Okay. So the conclusion of all this integral here, 1 over x to the p dx, this converges, or maybe let's say that, let's do the diverges. Diverges if p is in fact greater than or equal to, or sorry, less than or equal to 1. Okay? And this integral equals actually 1 over p minus 1 if p is greater than 1. Right? That's the conclusion here. And that's the full answer to that problem. Right? So it diverges if p is less than or equal to 1, and it converges if p is greater than 1. Now this fact is actually really useful when we talk about in multivariable calculus, well, at least in the class here, multivariable calculus, when we talk about things called p-series. Right? That's, knowing this fact here is incredibly, incredibly useful. Right? So with that, that's actually all the examples we had for today. So there's 10 more minutes. Is there any questions at all? Alrighty then. Well, with that, have a good afternoon, everyone. And sorry. And I'll see you on Friday. Take care.